Physics 2212, Lab 2, Charge Tapes Revisited. The purpose of this lab is to look back at the previous lab and create a more accurate model analyzing the real-world physics of charge. The model is the same model as last time, where we had physical pieces of tape and made a model using glow script based on the experiment. The results of this gave us the magnitude on each tape was determined to be 4.2 times 10 to the negative 9 coulombs. The magnitude of force of the electric field is 2.18 times 10 to the negative 4 newtons, and the magnitude of the force of gravity is 1.96 times 10 to the negative 3 newtons. This lab uses three key concepts. The first of the concepts is Newton's second law, which states that the net force on an object is equal to the change in momentum for that object over time. This is shown by the formula. The second key concept is Coulomb's law. Coulomb's law allows us to find the force of attraction or repulsion between two electric charges using the formula given. The final key concept for this lab is the gravitational force near the surface of the Earth, which is represented by negative mass times gravity. In this case, gravity is 9.8 meters per second squared. Some key assumptions we need to make for this experiment are that the tape behaves as a point charge with the charges located at the center of the tape to simplify equations. Each piece of tape needs to have the same total charge despite tampering, and we need to neglect air resistance. For the experiment, we have the system as tape B and the surroundings as tape A and pretty much everything else around it. The initial conditions for this are the length of both tapes is 0.2 meters. The tape is given a positive charge, as we found by putting it against a negatively charged pen, and the mass of the tape is 0.00196 kilograms. For the actual experiment, we suspended tape B between two objects and held tape A under it, which acted as a point charge, until it pushed up on tape B. Then we measured the distance between tape A and tape B when tape B was being pushed up, and we used that distance for our calculations. To start my calculations, I first found the gravitational force on tape B. The gravitational force is mass times gravity, and in this case it's 1.96 times 10 to the 3 newtons. Next, I found the separation distance when tape B floats. That was 0.009 meters. Next, to find the charge on tape B, we know that the electric force on B is equal to the gravitational force on B. Using the equation, we can find that Q is equal to 4.2 times 10 to the negative 9 coulombs. Using this, we can find the number of electrons by taking Q and dividing by the charge of a single electron. We found that there are 2.63 times 10 to the 10 deficient electrons. Using this as well, we can find the ratio of electrons over atoms. We can use the length of the tape of 0.2 meters and divide by 10 to the 10th, which is the length of an atom, to find that the tape has 2 times 10 to the 9th atoms. If we take our deficient electrons and divide by the number of atoms, we get 13.125. This is the code for the line charge model for Lab 2. At the top we have the function to find the electric field given a charged particle. In the middle we have the calculations to calculate the electric field at each individual location. And at the bottom we have the arrows to represent the electric force vector and the gravitational force vector. In the top right you can see the model illustrated with some values being printed at the bottom. Some similarities between Lab 1 and Lab 2 are that Lab 1 was about finding an electric charge using a point charge model, while Lab 2 is about finding the charge using an evenly distributed model, which was a line charge model. These gave different results. Some possible sources of error for this experiment are the charge on a piece of tape can fluctuate easily depending on the environment. The distance at which tape B begins to float may not be entirely accurate due to human error. Treating the tape as a point charge is a generalization and could also the final answers, and the charge on tape may not be evenly distributed across the entire surface. If we modeled our tapes as a point charge, it would have a smaller charge and less force due to the electric field. The magnitude on the new one would be less than the point charge. The reason these point charges differ is because the point charge is more an approximation, while the line charge is more accurate to the reality of the experiment.